Welcome back to video 2 of 3 of my final project presentation. Part 3 of the project explored the LSTM neural network. Starting with the vanishing gradient problem, the vanishing gradient occurs due to the simple RNN having a short-term memory. This unrolled RNN has layers at each step. During backpropagation, the gradients shrink, and that causes learning to stop and the beginning of a sequence to be easily forgotten. The gradient vanishes, causing the weight W to hardly update and stop learning. Here's another illustration when the weight is set to a value less than 1, such as 0.5. The input is multiplied by the weight of 0.5 raised to the power of the number of times the network is unrolled, providing a value that is near to 0 or vanishing. The exploding gradient problem is the opposite. Error gradients increase quickly during training and explode, causing a volatile network that can't learn. The weight values are amplified because they are multiplied at each step. The limitations of the simple RNN are short-term memory and having a very simple structure that cannot handle complex processing. This picture has the LSTM on the left and the simple RNN on the right. The simple RNN's basic design is a limitation. The LSTM solves the vanishing and exploding gradients by maintaining the gradient with the cell state, by using gates to determine what information to keep and what to drop by having multiple activation functions. There are 3 types of gates in the LSTM that are used for filtering or regulating information for the cell state. The forget gate decides what to remove or keep. This is what solves the exploding gradient problem. The input gate creates the save vector that is added to the cell state. The addition here is what combats the vanishing gradient problem. The output gate creates the output of the hidden state of the cell and the current cell state. Each gate has a sigmoid activation function containing values between 0 and 1. Values close to 0 are forgotten, and values close to 1 are saved. The flow of the cell state of the LSTM maintains the gradient at a steady level. The LSTM also provides memorized snapshots of the cell state. Information is removed by gates from the cell state when it is not relevant. This is how the LSTM processes through time steps to continue learning. Now we're on to part 4 of the project. For the dataset, I downloaded time series data of the General Motors stock price from Yahoo Finance for 5 full years from January 2016 through the end of 2020, excluding days the stock market is closed. This provided 1,258 data points with 7 attributes. First, I considered the network design with 3 LSTM layers, 2 dropout layers, 1 dense layer, and 1 output. Here's a simplified way of viewing the model, and here's details on the layers with the number of neurons in each. Next, I identified core parameters with 10% of data for testing 3 LSTM layers of 50 neurons each, 2 dropout layers with 20% to drop, a length of the time series input sequence of 60, batch size of 34, and 100 epochs for training. Then I started working in the Jupyter Notebook to import Python libraries, and I imported TensorFlow and models, and I imported the Keras time series generator, and I imported the min-max scaler. Then I loaded the General Motors stock price, and I showed the first 5 rows and did some exploratory data analysis to output some statistics. Next, I filtered the data to only keep the close attribute, and I graphed the close price. Then I set the length as 60 and identified the length of the dataset as 1,258. That's on a range of 0 to 1,257. Next was splitting 10% of the data for testing. That was 125.8 rounded to 126. Then I split the original data frame and showed the split index at 1,132. Then I split the data for training and moved it back 60 places because I need those for predicting the first data point in the test data. Then I displayed the first and last 5 records of training and testing. Next was normalizing the data and creating a time series generator instance with length of 60 and batch size of 32. Then I checked the length, it's at 1132, and I checked the number of batches generated. It was 34 because there were 1,132 data points in the training data set, moved back 60 places to get 1,073 data points, then divided by 32 samples equals 33.5, rounding to 34. Next, I defined X as the sample and Y as the predicted target for the train TS generator 60, and I flattened X and displayed Y. Building, training, and testing the model is next. I set the number of features at 1 for the close price. Then I defined the model as the Keras sequential model. Next was defining the layers of the model. The first, third, and fifth layers are the LSTM with 50 neurons. The second and fourth layers are the dropout with 20%. The sixth layer is a fully connected dense layer for the final prediction of one value. I compiled the model with an atom optimizer and MSE loss function. Then I trained the model with 100 epochs and visualized the model's performance after training. The loss value was at 0.1256 at the first epoch, then decreased sharply to 0.0151 at the second epoch, with a continuation of loss values gradually declining, then maintaining a value very close to 0 through epoch 100. Then I prepared for testing by defining a batch size of 1 and creating a time series generator for testing, and I defined a normalized prediction variable that displays 126 data points as expected. Then I checked the length as 126. Up next was converting the predictions to the true values, flattening and indexing for the data frame and creating the data frame. Then the prediction is displayed with 126 rows and 1 column. Then it's visualization time. Here's the graph after testing with the General Motors stock close in blue versus the prediction in orange. Testing finds out how well the model learns after training. Here's a better chart with the prediction and the actual values layered on top, and it looks really good. The model is performing great, predicting very close to the actual close price. Up next was forecasting with the entire data set, and the length was 60 data points in each input sequence, and a time series generator was set up. Then I trained the LSTM model with 50 epochs, and I prepared to forecast the future for the year 2021 with 251 periods. The first batch was 60 periods, and I defined the current batch. Next was a for loop to forecast. Then the data is transformed from being normalized back to true values. Then the original data set is displayed and the new timestamp index is created, defined, and displayed. And now the moment of truth. The forecast is plotted and it looks weird. The actual close values are in the top picture and the forecast is below, forecasting a sharp decline in the stock price, then slightly increasing, then leveling out around $22. Here's a combined graph. Well, let's see what it looks like with the actual close price in the same graph. I downloaded the 2021 data and uploaded it to the Jupyter Notebook and defined the variable and showed the first 5 rows. Then I narrowed the data set to only have the close price, and I displayed the data and the graph and the forecast values. Then a data frame with the close and forecast information is created, displayed, and plotted, and here it is, with the weird forecast and the actual close prices for 2021. The actual close values had increases and decreases, averaging $56 for the year. And the forecast had a decline and an increase, then leveling out to around $22. This project shows how the LSTM can solve the challenges typically seen in the simple RNN. Overall, the predicted results were good during testing, but the forecasted results were not. Stay tuned for the next video to see how the project is redesigned and potentially improved. That's all for video 2. I'll see you in video 3.